Hello and welcome to lesson number 5, probability part 2. So we're going to talk about a little bit more interesting probability situations that have to do with and or. We're going to start looking at the definition of and you'll notice right here the way that we write it out looks a little bit different because of this kind of like upside down U thing that we have right here. Different symbol, it means and, the mathematical and the way that I remember that this is the correct symbol is because if you were to put a line straight through it, it would look like the letter A, and starts with A. So that's one way of hopefully remembering it. Anyways, so this says the probability of A and B would be something as if we were saying when something falls into two or more categories, like a jack of hearts is both a face card and it's a heart, right? So that particular item falls into two or more categories, right? It falls into the face cards and the hearts. Then we have the situation here, probability of A or B. And how I remember this one is because if I went across with a straight line here, it would look like an O, or starts with O. So hopefully that also helps you remember which one's which. So you're looking at a situation when you were looking for two possible outcomes from the same event. So, like, if we roll a 1 or a 5, or, I don't know, maybe pulling out an ace or a 2 from a deck of cards, right? Those are different situations that could happen in the same event. So, we're going to start looking at these ones first, the ors. They're a little bit more work to do because of the fact that it's in two different events at once. So there's a little bit of a formula that goes with it. Okay, and here it is. If A and B are from the same sample space, so like a deck of cards type of deal, the probability of A or B happening would be equal to the probability of A plus the probability of B minus the probability of A and B. Now, we do call this and, it also means intersection of. So what this means is that we're going to be getting rid of a repeat when whatever this particular thing is intersects. And what I mean by that you will see in the example down here. But basically whenever it belongs to both categories at the same time. So first of all, you're going to need a calculator to do this. I have Desmos up and ready to go on my calculator. You can also use the school TI-84s. But here we go. We have a standard deck of cards. Okay. And it's telling us that we're going to be pulling one card randomly selected from that standard deck of 52 cards. We want to find the probability that the card is either a spade or an ace. So it falls into that or situation. So we need to use this formula right here. So the first thing that we're looking at is the idea of it being a spade. Now, I'm only going to do this for this one example, but you have all of these cards which are spades. Okay, in this situation there are 13 of those cards out of the total 52. So the probability of it being a spade is 13 out of 52. That would be our A situation. Probability of B being an ace, there's 4 aces. So that's 4 out of the total deck of 52. But we have this situation here when we look at all these cards together, because the ace that we're really interested in falls into these two categories. Let me do it this way. All right? It falls into both the spades and, oh, this is way off screen. My bad. Let me lay that back out again. All right, so the ace that we're really interested in, this one right here, falls into two different categories, right? It falls into both the spades and the aces. So it's literally in the intersection here of spades and aces. So when we counted all of the spades and we counted all the aces, we technically counted this ace twice. So we need to throw that card out now from our count for a probability. And that's what this little piece right here is telling us. It intersected somewhere in here at least once, so we got to get rid of that repeat. Luckily, though, that ace only shows up once out of the 52 cards. So we subtract 1 out of 52. Good news, these all have the same denominator, so we can just go straight across here. 13 plus 4 is 17, minus 1 is 16. And then we just want to calculate that real quick. 16 over 52. We'll do, it doesn't actually say what's a round to, so let's do 3 decimals here. It'd be 0.308. That's roughly a third, or 3 out of 10. So the card is either even or a red. All right, well, all the even numbers, right, you would have 2, 4, 6, 8, 10. So there's 5 of those. And there are 4 suits for a total of 20 out of 52 cards would be an even. And then red is half of our total. So that would be 26, out of 52. So using this formula again, probability that it's even, we said, was 20 out of 52. Probability that it's red is 26 out of 52. But the intersection, because we counted, let's say, the 2 as both an even and a red, right? That could have happened, or had to have happened. It could have been the 2. It's a 1 in 52 chance that we've got to get rid of. So let's see, if we add these, 20 plus 26 is 46, minus 1 would be 45 out of 52. And again, to 3 places. Now the nice thing with Desmos is all I have to do here is change that top number, 45, and we get 0.865. 0.865. Much more likely for you to either pull out an even or a red card. A much safer bet. It's like 8.5 times out of 10, almost 9 times out of 10, you're going to get either a red or a face card, an even card, sorry. Alright, so you've got one to try right here. Like, the card is either a club or a king. Pause the video and resume when you're ready to check. Okay. Hopefully you remembered how many clubs we have total, or each suit has total. Right, there's 13 in every suit, so there's 13 clubs. The number of kings there are 4. There's 1 per suit. But we repeat the king of clubs, so we have to subtract that out. That's 17 minus 1 is 16 over 52, and that actually matched with an answer from earlier, 0.308. Just as likely to pull out a king or a club as it is to pull out a spade or an ace. Okay, so so far this is our or, right? Something that could happen from the same situation. So let's look at some different things that could happen. Maybe we're looking at statistics. Okay, we have age groupings from 8 to 12, 13 to 15, and let's make that 16 to 18 just because we don't want the overlap there. 16 to 18. Okay. They want us to find the probability that a randomly selected person is either 13 to 15 years old or a girl. Okay. Well, what we need to know is the total number of people we're working with, and then we need to know certain things like age group totals and boy-girl totals, right? So let's just kind of go through that real quick. Using calculator, you can add these together, or you can do it in your head, whatever, right? 12 plus 14 would give us 26. 14 plus 13 would give us 27. And 11 plus 12 would be 23. These are the totals going this way for the age groups, going straight down. 6, 7, 37, 7, 8, 9, 39. Okay, and both of these should both total to the same amount right here. So it doesn't matter which one we add. I'm going to just go straight down. 10, 16, 6, 76. That should also give us 76. Okay, so now we know a whole bunch of totals. That really helps when we start looking at some of these questions, right? This one says either 13 or 15 years old. I'm sorry, either 13 to 15 years old or a girl. So when we look at the 13 to 15-year-old category, there's a total of 27 children in that category out of 76 total. Then you have the or a girl option. Right here we have the total of girls is 39 out of the total number of 76. But there's that intersection again, right? Here between girls and the age group, they intersect at 13. So we have to get rid of that overlap. Alright, so let's see if we were to add 27 plus 39 minus 13, we get 53 over 76. 3 over 76 to 3 decimal places is 0.697. So that's a very high probability of pulling out one of these randomly selected either from that age group or happen to be a girl. Your try here is to figure out if it's either going to be a boy or 8 to 12 years old. All right. Let's see how you did with this one. So either a boy or 8 to 12 years old. So boys total of 37 out of the 76. The 8 to 12 age group is 26 out of 76. Oops, I'm sorry. But the overlap here is the 12 boys that are in that age group. So if we add all this together, 37 plus 26 minus 12, oops, is 51. 51 out of 76 is 0.671. So although they are very close, it's more likely for the last situation to happen than the most recent. Okay, so that was the OR probability. Now we're going to look at something a little bit different. It still has to do with the OR probability, but this is what's called mutually exclusive events. This would be when we have two outcomes that cannot occur at once, like, for example, rolling two different numbers on one roll of a die, right? It's not possible for you to roll a 1 or a 5 at the same time. Those would be mutually exclusive. So the way that those work is we add the probability of A and the probability of B, because they're not going to intersect anywhere. It's not going to happen more than once. So when we look at this problem here where it says what is the probability of rolling a 3 or a 4 on a standard die, there's 1 3 out of 6 numbers, and there's a 4 out of 6, so that's 2 out of 6, which is 0.333. I don't even need a calculator. I can see that that's 1/3, right? So what this really means, right, that's a 1/3 chance of rolling that I should have prepared myself a second ago with a die. I don't know if I have any around here. Oh, I do. Okay, so I have a die here, right? Here's the 1, and here is the 4. So these take up 2 of the 6 sides. So that's, 1. If I did it again, this would be 2, and a third time would be 3. That's 1 out of 3. So it perfectly makes sense that we would be adding these particular things together because we did the 1 out of 6 and the 1 out of 6. So it just kind of proves that formula with this quick example. More exciting problems. Skittles. Who does not like Skittles? All right, a bag contains each of the following: 14 red, 19 yellow, 12 orange, 18 green, and 14 purple Skittles. Find the probability that you will pull out a red or orange Skittle. Right, so in this situation, we can't pull out both at the same time if we're only pulling one out. So we have the 2 different categories. This would become one of those addition type problems. So first thing we need to do is figure out how many Skittles we have total. 14 red, 19 yellow, 12 orange, 18 green, and 14 purple, for a total of 77 Skittles. Okay, now the number of red would be 14 out of 77, and the number of orange would be 12. Add those together, giving us 26 out of 77, giving us a 0.33, it's going to round up to 8% chance. A little bit better than rolling a 1 or a 4, right? Just a little bit. A yellow or a purple Skittle. Okay, well, there's 19 yellow. By the way, I had to make this yellow Skittles be the most because it's yellow. It's my wife's favorite color, and she was in the room when I wrote this. So, anyways, purple, we have 14. 19 plus 14 is 33. That gives us 0.429% chance. Alright, so I've got a couple for you to try. There's a little bit of a tricky one in here, but see if you can think about how that one works. Pause the video and resume it when you're ready to check. Alright, so a green or a red. So green, we know that there are 18 out of 77. Or a red, which there are 14 out of 77. That's a total of 32. Would be 0.416. A red or orange or purple. So there are 3 different things that could not all happen at once. So we just add all 3. So 14 red. Orange is what here? 12. Purple is 14. That's 28, 30, 40 out of 77. That's a 0.519% chance. The rounding there, make sure you round properly. And then finally, a non-orange Skittle. Well, all the Skittles total are 77. And non-orange would be all of them minus the orange ones, which there are 12. So that's a shortcut. Instead of adding them all together, you can subtract the ones that you don't want. So 77 minus 12 is 65. That was the kind of trickier one. So 65 out of 77. is 0.844. So you have a really good chance, if you're not a fan of the orange ones, when you first open up that bag of Skittles, for it to be a non-orange one. Or if you're a big fan of the orange ones, it's not the best, because if you wanted orange first, you don't have much of a chance of that happening. Or as good of a chance. Alright, so we're going 20 minutes now into this, so let's go a little bit faster here. We're going to look at independent events. These are multiple events, or the same event multiple times, that have no effect on future events. Like flipping a coin 3 times in a row. If you flip 1, does not affect flips 2 and 3. It doesn't become more likely to land on that particular side as it lands there. So, in that situation, we're talking about an AND event. Okay, so if A and B are independent events, the probability of A and B happening would be the probability of A times the probability of B. We can't have something happen more than once on, say, a coin flip, so it would have to happen multiple times in a row, in which case we'd be looking at the probability of those things together. In I can't say that word. We're multiplying here. All right. So what is the probability of flipping 2 heads, then 2 tails in a row? So there's heads and there's tails. So if we're talking about flipping a heads, it'd be 1 out of 2. But we're doing it 2 heads in a row. And then flipping 2 tails in a row. All right, well, there's 1 tails and then there's 2 tails. When we multiply all this straight across, 2 times 2 is 4, times 2 is 8, times 2 is 16. So flipping a heads, then a heads, then a tails, and then a tails, that's a 1 out of 16 chance, which is 0.063. Not the best chances of you flipping that all in a row. Alright, what is the probability of pulling out an ace from a standard deck twice in a row? Okay, well, there's 4 out of 52 cards are an ace. So you pull out one of those 4. Then you put it back in the deck, shuffle it back up. There's another 4 out of 52 still in there, right? Because you put it back and shuffled it up. So that's 16 would be the top number. 52 times 52 is 2704. So 16 out of 2704, 0.006. Not very likely to happen for you to pull out 2 aces straight in a row like that. All right. Wild Money in Rhode Island draws numbers 1 to 35. You play Lucky. Wow. You play Lucky 13 every week for 5 weeks. What is the probability that 13 is pulled every week? Okay, so we're doing this 5 times in a row. From 1 to 35, that would be 36 total numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, that's 35 numbers. I'm sorry. I'm not even sure what I'm talking about anymore. Anyways, 1 out of 35 total numbers. But you play it every single week. For 5 weeks. This is not going to be good. We're going to end up having a number that's not even close. Right? So we're doing 35 to the 5th power. 1 out of, ooh, this is a huge number, right? 5, 2, 5, 2, 1, 8, 7, 5. 52 million. So 1 out of 52 million. 1 out of 52 million. 521,875. Yeah, it's coming up with something to the -8 power. So if you play Lucky 13 every single week for 5 weeks in a row for that number to show up every single time, not very likely. All right. By the way, this was 10 to the -8, so there's 5 more zeros in here. Okay, enough about that. Find the probability of flipping a heads twice in a row, then rolling a 6 on a die. All right, you try that out. Pause the video and resume when you're ready to check. All right, heads twice in a row, no problem there. And then after that happens, we roll a 6, which is only 1 out of 6 on a die. 2 times 2 is 4, times 6 is 24, so there's a 1 in 24 chance that you could do all those things in a row the way that you plan it out. Right, imagine you walk into class one day and you just like declare to everybody, I'm going to flip a heads twice in a row and then roll a 6, and then you do it. That's the chances of that happening. All right, let's say you bought a bag of mixed candies. There are 5 flavors and 5 of each flavor. The first candy you pull out is your favorite candy, so you put it back in to save it for later. Duh. What is the probability that you pull the same flavor out 3 times in a row, even though you didn't want it at all? Well, if there's 5 flavors and 5 of each flavor, that would be 25 total flavors, right? But we can even reduce that further, because if there's 5 of each and there's 5 flavors, we can divide each of those evenly. So basically there's 1 out of 5 for each flavor. 1 out of 5, 1 out of 5, 1 out of 5 for the 3 times in a row. So there's one out of 125 chance of pulling out your favorite flavor every single time in a row, even when you put that back into the bag. That's a 0.008% chance of happening. Most likely it's because you put it into the bag and then you probably just pulled that same one out without mixing it up. That's probably what's happening. So that's it for that lesson. Apparently that's it. Hope you enjoyed that. That's some different probability that we saw from before. Different situations and different types of formulas to use. The key is remembering what situations and what formulas to use at which time. So good luck with your studies, and if you have any questions, let me know. You can post them on this video, or you can email me later. Bye.